To this point in this portion of the course, we've been investigating, we're starting to investigate rotating systems. To start that out, we developed sort of a hybrid coordinate system called the tangential centripetal coordinate system, which really is a linear coordinate system, but is used to describe the motion of things that are moving in circles, in uniform circular motion or in non-uniform circular motion. You can use it to describe the motion of things undergoing curvilinear motion. And that's a very useful coordinate system, but we need to develop a coordinate system which is truly rotational. That it is not linear in any fashion, but of course, if it's going to correspond to real motion, we're going to have to translate it to linear motion, which we will see. But to do that, I find it first useful to talk about things which you may know or may think you know. So things such as radians. We know kind of what a radian is, right? It's another way of expressing angles besides degrees. For degrees, we would divide a circle up in 360 equal units. For radians, I should say, we divide it up into different units. If you're in my class, you have been through Cal 1, which means you've been through trig or pre-cal, and means you at least have a working knowledge of radians. But what I've found is pretty typical, and what I certainly found in my own academic journey, is when I got out of trigonometry in Cal 1 and even Cal 2, I knew how to work with radians. I knew how to convert radians to degrees, and I knew when I needed to use radians, but I didn't really have a good understanding of what a radian was. So to try to get you some understanding of that, I've drawn more or less a circle, or I've freehanded it so it's not fantastic, but this circle has a radius r, and I've cut a string that is basically the same length as the radius. And I'm going to use this string to measure distances around the circle. I've got to use a string because I've got to be able to bend it. I've got a curve. Okay, fair enough. So if I put my string here and I curve it around, I can kind of come up with the arc length. Remember, the distance around a curve is called the arc length. Arc length that is equal to 1 radius. It's about there. And we're going to go over here, do the same thing. We'll see how well I did drawing the circle and cutting the string. I can already tell you it's not great, but this looks okay, actually. Somewhere about there. And keep on going, etc., etc. I'm going to go one more. And of course I can do this all the way around. For future purposes, let me draw in the line that delineates the half circle. And it looks like I didn't do too badly there. So if I go back to this first one, I've got this distance. Remember, the mathematical symbol for an arc length is usually S. This particular arc length is equal to R. So if I do that, if I move around that circle 1 arc length of R, I have described an angle. In other words, I have rotated through an angle, right? I can't move without with reference to the center describing this angle theta. For the particular case in which R and S are the same, the arc length is equal to the radius, the angle that I have described is 1 radian. So this is actually where radian comes from. It's got the word radius embedded in it because that's what it means. It means you've moved around the circle 1 radius. I could go on from there, right? This would be 1 radian, which corresponds to an arc length of 1 radius. Then I could go another one. I could go 1 more radian. So I've rotated through a total of 2 radians, which means my linear distance here is it's 1 arc length of 2 radians. I'm not saying that very well. Let me back up. Moving through 2 radians means that I've moved linearly. I've walked, if I'm walking around the circle, an arc length of 2 radii. And then I can go farther. I can go to 3 radians, which means my arc length now is 3 radii. And then when I get to this point, that's a pretty important point halfway across the circle. It might be reasonable to ask, okay, through how many radians have I moved here? And it turns out that this point, if I get here, I've moved through about 3.14 radians, or pi radians. That's why pi turns out to be very, very important. Pi turns out to be the ratio between the diameter of a circle, the arc length of a circle, and its radius. So, interestingly enough, this is pi radians. And if I keep going along, I'm going to get over here. If I move around the whole circle, this would be about 6.28 radians. That is to say, 2 pi. So, we also, in addition to all this, and probably in trig or pre-cal, learned this formula, which we call the arc length formula. S is equal to r theta, as long as theta is expressed in radians. This is how you determine how far around the circle you've moved if you've rotated through a certain amount of radians. Theta expressed in radians. Most of you also know that the circumference of a circle is equal to 2 pi r. What you might not have ever put together is that this is just the arc length formula for a particular theta of 2 pi. Right? I move around 2 pi radians, and that means I'm plugging in for theta here, 2 pi r. This is just the arc length formula. All right, so we have this crosstalk here between a true angular coordinate and a linear coordinate. S is a linear distance. This is measured in meters. So I've got this formula which relates the linear distance around the circumference of this, or around the outside of this, to the angle through which I've moved. We're going to find that there are always formulas that relate the linear quantities to the angular quantities. This is just the one most of us know already. So that's what a radian is, and that's what it does for us. So what I want to do now is start to talk about other ways to express angular variables. And what I'm going to do is make a chart here side by side, where I have my angular quantities here, my linear quantities here. We know the linears, most of them. We need to talk about the angulars. Where did we start with linear motion? We started by talking about a position, which we usually denoted as x. X, of course, has units of, in this class, meters, or some sort of linear measurement. Our position for angular, we've already seen it, is a theta. Right. Now, of course, just like with linear position, I'm going to have to define an origin here. This is the convention. I define my origin here, and then I take the counterclockwise direction as positive, the clockwise direction as negative. That's the convention we'll follow. Do you have to follow it? No, as long as you know what you're doing. But if you want to be able to communicate easily with others, probably best to follow what everyone else is doing, at least mathematically. So if we start here, we can move counterclockwise around the circle, and that is known as the positive direction. This will be my origin. So any theta I list will, by default, be measured around the circle from here, counterclockwise direction. Unless, of course, it's a negative theta, then I measure it clockwise. So once I had the idea of a position, I also recognize that position can change. Well, nothing different over here. This is delta theta. Of course, a delta x and an x are both measured in this class in meters. Theta and delta theta are going to be measured in radians. Now, let me caution you, a radian is not really a unit in the same sense that a meter is a unit. Very often we see radians just kind of disappear from unit consideration. And that's because radians aren't really units like a meter is a unit. Recall that trigonometric functions must be dimensionless. So if I'm going to talk about a cosine of theta, theta actually can't have a true dimension. So radian is, you can think of it as sort of a virtual dimension. That sounds very science fiction-y. But it's at least what we can say is it's not a unit in the same sense that a meter is a unit. All right, where did we go from there? Well, we developed the idea that this process, going through a displacement, takes time. And if I form, I'm just going to use the full version here. If I form dx dt, of course, you can form delta x over delta t. But if you've had some calculus, you let delta t shrink down to an infinitesimal and it becomes a true derivative. We define this as the velocity, the change in position per unit time, units of meters per second. We can do the same thing over here. Undergoing an angular displacement takes time. And so I can talk about d theta dt, the angular velocity measured in radians per second, with the same stipulation that radian is not a unit in the sense that a meter is, but a second is. And so sometimes you see this expressed just as a 1 over seconds, or we'll call that a hertz later. But sometimes you'll see this expressed like that, especially when we start talking about angular frequencies later in the course. So we need a symbol for this. The convention here that we started is to use Greek letters for angular quantities, Latin letters for linear quantities. So I'm going to use a lowercase omega. This looks like a W. I promise you it's not. This is a lowercase omega, and if you call it a W, I will correct you, because the symbolism, the symbols, the language, however you want to say it, is very important. Most of you know the capital omega. This is a lowercase omega. I do not write W's like this. I write W's like this. So if you're in my class, you're looking at my handwriting. If you see this, that's not a W. This is a W. This is an omega. All right, so the omega, the angular velocity, is going to be d theta dt expressed in radians per second. And of course, delta theta over delta t works just fine in the right circumstances. We went farther, right? A is then equal to dv dt, or second derivative of velocity with respect to time. Okay? We need an angular acceleration. Again, using the Greek letters, I'm going to use an alpha, which is going to be equal to d omega dt, or second derivative of angular position with respect to time. D omega dt is my angular acceleration alpha. We had the linear acceleration a. So once I have these, I can actually do a lot of things. Let me just show you how this works, because, well, not worrying about the because right now. Let me just say that most of the equations I've developed so far, I can now use with angular quantities, just like I did with linear quantities. For instance, kinematic equations. What did I have? V final is equal to V initial plus AT. Just by looking at the analogs between the Latin and the Greek, I could actually form this in angular form. Omega final is equal to omega initial plus alpha t. Delta x is equal to v initial xt plus 1/2 axt squared. Well, delta theta is equal to omega initial t plus 1/2 alpha t squared, and so on and so forth. Actually, all of the equations I've developed so far have angular forms. When we start talking about energy and momentum, we're going to be really specific with that. We've got angular momentum. We don't have angular energy, but we do have energy associated with rotational motion as distinct from linear motion. So we'll talk about that stuff when we get there. But for now, I just want you to focus on the fact that I can just write down these equations by substituting the Greek letters for the Latin letters, and I have actually formed the correct equations for rotational motion.